Here we are learning mathematical analysis of recursive algorithm by using some examples. For the first example, I will take computing of a factorial number. That is, f of n is nothing but n factorial. Here n is actually a non-negative integer value. Okay, to solve that formula, we are using here n factorial is nothing but we are multiplying the number from 1 to n values. When you multiply all the numbers between 1 to n, you got the factorial of n. Now, to simple way, I can say it's nothing but I am multiplying from 1 to 2 to 3, 4, 5, up n minus 1 to n. Okay, we can simply write here n is nothing but n minus 1 factorial into n. I just change this formula like this way. Okay, when n value is greater than 1 here. Okay, whenever the n value becomes 0, 0 factorial is nothing but 1 by the definition. A simple way of calculating this simple way of calculating this factorial is actually factorial n is nothing but factorial n minus 1 into n. When you apply this formula, when you use this formula for finding the algorithms, you are getting recursive algorithm. This is a recursive algorithm for factorial here. Factorial algorithm is written like f, which will take input n. It will compute the factorial of n recursively. N is an actually non-negative integer value, and this algorithm returns value of n, that is factorial value of n. How actually it will works? If n value is 0, whenever the n value becomes 0, it will return 1. If n value is greater than 0, okay, in that case we have to multiply factorial of n minus 1 with n. Whenever this n value becomes 0, n minus 1 value becomes 0, our recursive algorithm stops. Now we do the analysis for this algorithm. As the algorithm tells you, as the n size increases, this algorithm execution also increase. So n is an indicator for the algorithmic input size. Okay, here the basic operation is nothing but this multiplication. F of n minus 1 into n. This is actually the basic operation of the algorithm. Okay, and the execution of that basic multiplication is nothing but m of n. Okay, since the function f of n is computed according to the formula, now we know that how to compute the factorial here. Factorial of n is nothing but n minus 1 into n. That is nothing but factorial n minus 1 into n for n is greater than 0. Now, when you apply the same formula for the number of times this multiplication works. Okay, here m of n is nothing but the number of times this multiplication works. Can be calculated using m n minus 1. Here you have to this is used for computing. This multiplication is actually used for computing factorial of n minus 1. Okay, and this 1 is actually to multiply the last f n minus 1 by n value. Okay, one execution for the last multiplication, the remaining m n minus 1 multiplication for the f n minus 1 operations whenever the n value is greater than 0. If you see this formula here, we need m of n minus 1 multiplication to compute this factorial n minus 1, and one additional multiplication is for multiplying by n. Okay, now here we need to an initial condition. we need an initial condition that tells us the value with which the sequence starts. In this recursive algorithm, we need the initial condition. The initial conditions are generally the statements or the lines which will stop the recursive call. Okay, most of the time it is in our algorithm here, it is if n is equal to 0, return 1. This is the initial condition. Whenever it reaches initial n is equal to 0, this whenever it is true, our execution stops. If you see here properly, there is no any multiplication whenever there is an initial condition is true here. Okay. So we can identify the number of multiplication here by using formula m into n, so m of n minus 1 plus 1. Okay. When n value is greater than 0. If n value is 0 here, it's nothing but 0 because there is no any multiplication. When you simplify using backward substitution here, when you use the backward substitution, you may found like this one. M of n is nothing but m of n minus 1 plus 1 here. Okay, here I am substituting m of n. Okay, one more time here, you have to substitute m of n minus 1 is nothing but m of n minus 8 is nothing but m of n minus 2 plus 1 here. So I will apply this formula, this here on the m of n minus 1 here. I just apply this formula on this m of n minus 1, and which will result n minus 2, m of n minus 2 plus 1. See the area and plus 1. Whenever you simplify it, you got m of n minus 2 plus 2. Again, you apply the formula on here. M of n minus 2 is nothing but m of n minus 3 plus 1. When you apply this formula on this area, you got m of n minus 3 plus 1 and plus 2. The final result is m of n minus 3 plus 3. If you see properly here, one pattern will be created. Okay, m of n minus 1 plus 1, m of n minus 2 plus 2, m of n minus 3 plus 3. One pattern will be created. Here, whenever this second part will be increased to 1 to 2, 2 to 3, after the last part is also increased 1 to 2, 2 to 3. Here also the term will be increased. So instead of number, I can make it a variable called as I. So we got here formula, we got a pattern here, m of n minus I, instead of 1, 2, 3, I can write here I. M of n minus I is plus I. This is the formula I applied here. When we use the backward substitution, when we apply the backward substitution, it looks like this way. M of n is equal to m of n minus 1 plus 1. Here the number of recursive techniques for f of n minus 1 plus multiplication n. One is for multiplication n. When you apply the same here, it's nothing but m of, okay, when you written like this one, m of n minus 2 plus 2, m of n minus 3 plus 3. It's nothing but m of n minus I plus I. When you go further, you got m of n minus n plus n. Here it will remove the n minus, and you got the final result n. That means our algorithm is linear function.